All right. Hey everyone, welcome to the stream. Sorry, just gonna adjust this. Okay. So I streamed last night, and although I didn't do much in terms of programming, I did get a lot of get a lot of interesting reading done, and I have some more to do tonight as I collect information and get ready to implement the VIA chip. Let me just load up Vectrexy here. So yeah, I'm gonna continue doing that. Okay. Yeah, I'd hacked this in yesterday to get a kind of an idea for how many reads and writes occur on the different registers, and I got that down in my notes here. So that was interesting. But yeah, I'm gonna just kind of continue where I left off yesterday. So I was reading internal.txt here, and I was reading about how the VIA chip works in terms of the vector drawing hardware. So I looked for this yesterday, and there's supposed to be an image that goes with this, and I can sort of see, I couldn't find the image yesterday, but I can sort of see like what it would show, and I might actually end up drawing one myself to sort of understand a little bit what the multiplexer is connected to, how it's connected, how it's controlled, and all that. But basically, this information is all here. I was thinking about this morning. I was thinking about how there's this y-axis integrator channel, x-y-axis integrator offset, and trying to understand what that means. I think the y-axis integrator channel is, well, I was thinking about like concretely what this actually boils down to. Down here, that's what I was looking at yesterday. There's a computation for the kind of change in x. So x is at some place right now, say the x or y position on screen. And basically, there's like this input value and this offset value, which are both fed, and that's what this I think the input is this integrator input. So integrator input versus integrator offset. And basically we subtract these values. So I'm not sure what that's about. That's something I'm trying to understand here. So I'm going to keep reading and see if this clears up for me. But like, why do we have these two values? I see why that we compute them. I see them used here in this see here, Vn minus V offset. It all comes from this integration here. You see, let me reread this. So before the input to each integrator is an analog switch. This switch is connected to the ramp line from the 6522 P. So this is the VIA chip, port B, bit 7. So that corresponds to oh no, I should be looking at, where is it? My machine rebooted, so I lost all my, move to other view, all my settings that I had, or at least some of them. Okay, here. So yeah, the ramp line here. So that's the ramp line here. Okay. When the switch is closed, the integrators will integrate the value presented on the input. And when ramp is negated and the switch opened, no integration action can occur, and the integrators will hold their current value. Okay. So this bit here basically controls whether the integrator will be integrating the input value or just hold that input value, I believe. That's what it seems to be saying here. The output will follow the following form. For the XY integrators, R is 10,000 and C is this constant here. When we fill the numbers in, we get starting to see what this means here. Assuming that the full deflection voltages, I don't know, we can calculate the beam movement. So yeah, still not getting exactly what the input versus the offset is. Let's go reread this again. This is the DAC. This is the most crucial part of the vector block. It is connected directly to port A of the 6522, and the DAC takes this 8-bit digital value and converts it into an analog signal proportional to the value of the byte present to the DAC. It takes this digital value and converts it to an analog signal proportional to the value of the byte presented to the DAC. And it's saying here that the DAC's output will be that value in port A minus offset times a constant. So I'm not sure what offset is here, and I'm not sure what the constant is. Be warned, there is no enable control on the DAC, so whatever value you present will be converted. The DAC output connects to the input of the multiplexer and the input of the x-axis integrator. Port A, which feeds the DAC, also connects to the sound chip. So when you write to the sound chip, make sure that either or both the blank and RAM signals are not asserted. Otherwise, you may draw crap all over the CRT. Okay. Basically, all I'm understanding there is, since it's also used to send data to the sound chip, when you want to do sound, make sure to disable the stuff that does rendering, that does drawing. Makes sense. Now the output of the DAC is connected to the input of the multiplexer. One half, the other half is used for A to D conversion of the joypad potentiometers. The multiplexer takes the input signal and switches to any of the 4 output lines. The input signal is only ever connected to one output line at any one time. The multiplexer has 3 control inputs. The first, the enable signal, comes from the 6522A switch line from port B bit 0. Okay. When this line is active, the input pin is connected to the selected output pin, which is based off these two here. So these 2 bits select one of the 4. Okay, these bits are used to form a 2-bit number. These inputs are used to decide. So yeah, so these decide whether it's the y-axis integrator, xy axis integrator offset. Okay. So let's see here. X-axis integrator. Do we get into the offsets later on? No, maybe I'll just finish reading this. Maybe it'll become more clear, because I see this bringing it all together here. So let's just keep reading from where we left off yesterday. Ramp, digital active low. So as mentioned above, the ramp signal controls the integrator integration time described in the previous section. This line is an active low signal and is connected to the 6522 PIA port B. I don't know why they call it PIA here and via. Anyway, port B, bit 7. So this line, they say it controls the integrator integration time. But really, is that time? As described in the previous section. Yeah, I see ramp time here. I guess what it means is while ramp, like the ramp time just means while this ramp bit is engaged or activated, right? So I guess that's what ramp time means. You know, while it's 0, which is seems to be active when it's low, so while it's 0, it'll keep integrating. Okay. Okay, 0. Digital, also active when it's low. So where is 0 again? 0. Okay, seems to be controlled here, probably the third bit. So 0. This line is connected to the CA2 line for info CA2. All right. See the section 6522. See that's for info on how to set this line up. As with ramp, it is an active low signal during any during any integration operation, this line must be set to the inactive state. When active, this line will cause the integrator output to be set to 0 volts, which will be the center of the screen. Okay, so it's a way to force the output to 0. This line should be activated before any line drawing sequence to set the integrators to a known value. The integrator output value is held by a small capacitor, and this will leak charge. Basically, the result is that over a period of time, when the integrator is not in ramp mode, its output will slowly fall to 0. That's interesting. So after drawing a sequence of vectors, it is best to zero the output to give a solid reference. When active, this line will cause the integrator output to be set to 0, which will be the center of the screen. This line should be activated before any line drawing sequence to set the integrators to a known value. The integrator output value is held by a small capacitor, and this will leak charge. Basically, the result is that over a period of time, when the integrator is not in ramp mode, meaning it's not integrating, so nothing is writing to this capacitor, its output will slowly fall to 0. So after drawing a sequence of vectors, it is best to zero the output to give a solid reference. Okay. Z-axis signal. This signal controls the Z-axis of the CRT, the brightness. It is set by I should correct some of these. By setting the multiplexer to the z-axis setting and writing a value to the DAC. This signal is connected to a sample and hold circuit. So you can switch the multiplexer away from the signal and it will hold its value. As with the integrators, C37, the sample and hold will slowly drift towards 0. So every now and then it will need to be rewritten. A good idea would be to write this value once for each object being drawn, or once per group of screen refresh. If you are using a constant brightness, of course, or once per group of screen refresh if you are using a constant brightness. Of course, if your vectors are of differing brightness, then you will need to set this value for each vector anyway, right? Okay. So I guess I would have to simulate the fact that it's the brightness slowly decays if it's not being set. There actually, might be games that even rely on that for the look. Like drawing most important objects first to the least important, knowing that there will be a decay in the brightness. Although that might look weird, so maybe the games didn't do that. Anyway, and blank. So that you don't need to change the brightness when positioning the CRT beam on the screen, you can use this line to temporarily blank off the z-axis signal. Temporarily, okay. When negated, the z-axis signal will return to its old value. So it's kind of like an override. Basically, if you do blank, there's no drawing. Bringing it all together. The main basis of the vector drawing, as we've seen, is the x and y integrators. The z-axis brightness is a passive system and easily understood. Just in case the technical bit has lost you here, here's an analogy to explain the integrator system. We'll convert all of our electrical system to some household plumbing. Voltages will convert to water pressure and current charge to water flow. So our DAC is a tap, and the value we write to it is the water pressure behind the tap. An integrator can be thought of as a water tank. The screen deflection is measured by the level of the water in the tank. So when we set the DAC values, we set the water pressure at the tank and inlet. The ramp switch controls the on-off of the tap. So the higher the pressure, XY integrator values from the DAC, the faster the water will flow into the tank, and the faster the level will rise, i.e. the water level is the vector position. And the faster the level will rise, i.e. the water level is the vector position. So, okay, we have two tanks, X and Y. So you can see we have two ways of regulating the water levels. The water pressure and the amount of time we leave the tap on for. Right, because we can go high pressure, low time of tap, or low pressure, longer time of tap. Halfway down the side of each tank is a valve marked 0. We always start with our tanks half full, and after we've poured our water in, we can open the 0 valve to dump out excess water and bring ourselves back to the 0 point, the screen center. But our system has a twist. We can set the input taps to a negative pressure. Just fix that. To a negative pressure and suck water from the tank. And, we can set the input taps to a negative pressure and suck water from the tank. And when we open the 0 valve, water will flood in to fill us back to the midpoint. Our system also has a few minor problems. Our tanks have holes in them and slowly let the water out back down to the middle level. And the pressure we set on the tap slowly fades away. So we must always zero and set the tank pressure before a flush fill cycle. It's in this manner that we can push the CRT beam around the screen to create the vectors we require. Oh, that's interesting. Maybe after reading the above, you now have a pretty good idea about how to draw vectors, or maybe you weren't really interested and skipped it. So here is the info on how to draw a vector. All right. Hi, Michael. Michael C. How's it going? I'm reading some docs. I'm going well. Thanks for asking. A little bit tired, actually. I think this is the first time you joined the stream, right? Well, thanks for joining, man. So yeah, I'm in the process of reading how the Vectrex's vector drawings works at the lower level, so that I can start implementing it. I'm excited to get back into actually programming this, or just programming. I've just been reading since yesterday, but I kind of need to make sure I understand how all of this works before I start writing code. I'm starting to like form an idea of what I'm going to be doing to see all this. Most likely I'll just use OpenGL and start off with some basic, even maybe immediate mode drawing, just to see if I can get something going with all this information. But I don't think I'm there just yet. So if you don't mind, I'm going to keep reading. I'll read out loud, but feel free to write or ask questions or whatever. All right, so how to draw vectors. So let's see. Step 1, set the blank bit to 0. It should already be set to this to stop it dribbling crap on the screen when idle. Right. Set the 0 bit to 0 to clear the integrators. Yeah, so this means actually enabling the 0. Set the ramp bit to 1. So this means we want to start drawing. So this enables the integrators. Set the 0 bit back to 1, meaning we don't want the output to be 0 anymore. Just gonna put a little note here. Disable zeroing output. Enable the multiplexer and select Z-axis. Okay. Write your vector brightness to the DAC. Select the XY axis integrator offset and write your value to the DAC. This can be used to scale the XY axis up, down. Scale. So we subtract the offsets. So if it's 0, then it just uses the value we put on the integrator itself. or we can use it to, like, why would you do that? Select the XY axis integrator offset and write your value to the DAC. This can be used to scale the XY axis up down. It's weird. Okay. 8. Set the blank line according to whether this operation is going to be a draw or position operation. Right. So we want to reposition. We want to keep blank enabled. Or if we're going to start drawing, we want to disable the blanking. Select the y-axis. Select the y-axis to the multiplexer and write your y-axis vector velocity value to the DAC. Okay, so that's a good way to think about it. As a velocity. It's how, as he was describing earlier, it's how fast the water flows from the tap. That's the integrator input. Then disable the multiplexer. Write your x-axis velocity velocity to the DAC. Right, because when you disable the multiplexer, then it is the y-axis value that's used. Okay, just wanted to check something. So we disable it here. Disable the mux, and then writing the value ends up being the x-axis velocity vector. Okay, set ramp to 1. Like, I'm wondering, can this be red? Not sure. I don't think so. All right, set ramp to 1. Again. Oh, okay, it's because of this next step. Now vector is now being drawn. Then you set the ramp to 0 to stop drawing. You potentially loop back here. That's why you would set it back to 1. Okay. This is just a good, like, general algorithm for how you'd want to draw on the Vectrex. Then vector has finished. Set blank to 0 to stop any more info being drawn on the CRT. So now that we've finished. The above can be run in a loop for each object or the whole screen. I don't know how the exec ROM does it, but I would run the 1 to 14 sequence once for each object, i.e. the 8 to 13 loop for the components of the object. This would ensure the repeatability of object positioning, as each object is always placed with references to the 0 rather than the last object drawn. If you don't do a 0, it's likely that errors will build up and your objects may appear wobbly or jittery. That makes sense? Although I wonder how much time you lose waiting for the vector position to go back to 0. That's something he's not talking about here, but like, from what I read, it's not like the vector beam doesn't immediately go back to 0. It takes a certain number of cycles, so I don't know if you have to wait in between to make sure that these things happen. Parts 5 and 6 of the sequence can be omitted if you're only positioning the vector ready for drawing. Right. You don't need to always set the brightness. And if you're only positioning, we don't really care about it. Now comes the tricky bit. Just how do we calculate the values for x and y velocity, xy integrator offset, and how long do we make the ramp pulse? The length of the ramp pulse is critical if the screen is to appear stable. You must disable the interrupts during the vector drawing cycle, as an interrupt occurring when ramp is active would alter the length of the ramp pulse. Right. As I see it, there are three possible ways to drive the system, all assuming that the XY integrator offset is constant. You can use it for zoom in out effects. Oh, I see. Okay, so that's what he means by scale. Because it's a constant that gets subtracted. Like you take the current velocities, values your game is writing to move the beam, and then you can use a constant, which is this offset, to subtract the velocity value. And if you put you can even put a negative number in there, so that'll actually add, or a positive number will subtract. So this allows you to control the speed of the beam in a constant way globally. Okay, so that makes sense. The most likely way the exec ROM does it, in my honest, humble opinion, we have a fixed length of ramp. We have a fixed length of ramp pulse for all vectors. Okay, so ramp would always have a fixed amount of time. So we draw for a fixed amount of time. Then, with the 8-bit DAC values, we have a 255 unit resolution on vectors in both the X and Y axis, right? This doesn't mean the screen resolution is 256 by 256. Depending on the values used for ramp time and XY integrator offset, a 255 unit vector could be extremely small or very large. It's because everything is done relative to the last integrator position. These are not English sentences, but anyway. This doesn't mean the screen resolution is 256 by 256. Depending on the values used for ramp time and XY integrator offset, a 255 unit vector could be extremely small or very large, right? I think it should just be because everything is done relative to the last integrator position. I reckon this method involves the least calculation. You fix the ramp and then set the unit length with the XY integrator offset. Right. So I think what I think he means here when he says fixing the ramp is you have a fixed amount of time to draw. Like when we come back here, when you're kind of planning out how you're going to do the drawing, you fix your ramp time. Where is it? Yeah, well, the ramp time is the time, the integration time, which is this here. So it's basically how long the beams are drawing for. So he's saying, you say, I know how long I'm going to have to draw. Like I have this amount of time to draw this frame. Given that I know I have that much time, and for all vectors. I guess he means for each vector. Or no, yeah, I guess that's what he means. I guess that's what he means. It's like if we know the ramp time is fixed, then we know, like, basically it's like saying that every time we draw a vector, it always takes whatever this fixed amount of time to draw, and we can vary the length of our vectors by messing with the offset. Like obviously the integrator values themselves, like the speed. So we just play with the speeds. Like if we want a long line, we just increase the velocity or integrator input values for x and y. And if we want to do scaling, we can do that with the offset value. And what he's saying is that we have a resolution of 255 units. What he's saying, that means that when you want to draw a line, you can put any value from 0 to 255 and think of it as a length for x and for y. Okay, that's what this means. So that's like a really simple way to do it. We say we're going to ramp pulse. We're going to pulse the ramp for a fixed amount of time. And we choose that time based on how many vectors we need to draw and the fact that we need it, if it's too short, like you can think of it as, should I put 255 in there for x? I want, and the offset is 0. I would like, let's say, the ramp time for that one vector to be enough to maybe draw a full screen's worth of vector, like a full line, say screen width line. If you know that, then after that you can say, okay, now I can simply divide that up into 256 parts, and that's like almost like and that is basically our each piece is how long the vector can be, and we base all our math on that. That makes some sense. Number 2, we have a lookup table of x, y values depending on the direction that we want to move. You could calculate the values, and these are all scaled for a single fixed unit length vector. We then have a choice of either varying the ramp length or xy integrator offset to produce the length of the vector we require. We just multiply the values of x and y integrator settings for the fixed unit length by the length we require. Okay, sure. I don't really need to understand it that much. All of this for me is mostly, like, I'm reading this as, if I were to do this, no, what I mean is understanding how different ways of doing it helps me to understand underneath what the hardware is trying to do or how it works so that I can emulate it. So the most complicated way, we can vary all of the variables, but God only knows how we would calculate them. We would have 4 variables. Okay. So he means the x and y integrator values, the fixed offset, and the ramp time. Solutions 1 and 2 look the most promising as they restrict the number of variables we have to calculate. Using a fixed value of ramp would seem the easiest thing to do so that we avoid any problems of, sorry, just got a message and distracted me. So using a fixed ramp would be the easiest to avoid problems of CPU cycle counting to get the required ramp settings. We would need good control of the ramp time resolution, which is awkward, though not impossible in software, especially when there is no hardware timer. Without access to a Vectrex and some development tools to write some test code, I cannot test any of these theories and work out conversions from DAC values, times to screen positions, as I don't know what the full screen deflection voltages are. I would assume that the max-min integrator values will correspond to the max-min screen deflection values, or maybe the max-min value is off-screen, but by how much? Warning, don't go poking around in the insides of the vector deflection circuitry. The logic board only contains low voltage circuitry, but the voltage chopper for the vector deflection circuit produces voltages of around 5,000 volts. You have been warned. When I have time to disassemble the exec ROM, I can clear up once and for all how the exec draws vectors. Okay. So that brings me to the end. And so actually this has cleared up quite a bit. And I think I can like start at least writing some code for this, and or organically try to get to where we need to. So let's see, how should I tackle this? One thing I was thinking was, okay, let's do this. Let's at least start putting in variables for all 16 bytes, all 16 registers. Okay, let's do that. I'm gonna just undo the changes I made in this file. So Michael, Michael C, what brought you to my stream, if you don't mind my asking? Okay, so let's just reset these changes here. Michael C says he likes to check out emudev streams. That's cool. Are there, I've looked around for other emudev streams and haven't found, have I found any? Well, no, I mean, there's Ferris, of course. Ferris doing his, but apart from Ferris, who started with his Rustual, was it Rustendo 64 and now Rustual Boy, haven't found many others. Yeah, you say there are some. If you know of any that stream sometimes, send me them, because I'd like to catch them as well. We got to try and grow the emudev community. Okay, so Michael C says he's probably seen about 5 and they hardly stream at all. So I guess people get started on projects and then eventually either give up or either they give up or they don't want to stream it anymore because it's maybe too challenging or something. I don't know. Yeah, Ferris is definitely very active and has an awesome stream. Okay, so right now I have this array of 16 bytes, which we want to get rid of, and we want to start replacing that with these actual ones here. So I'm just going to move these back to the other view here. And I'll put them in like the same order and we'll go with that. So this would be, yeah, B, basically. I'll probably rename these. I just kind of want to start writing them and then I'll see. So this is the DDRB, data direction. Like, yeah, normally if I look at my CPU here, yeah, I shoved them in a registers class. Yeah, that's fine. Okay, let's just keep going here. So this is T1C, the counter, T1CH, T1CL. So this is low and high. Like, I'm wondering if I should make this the 16-bit counter that it's supposed to be, or make it 2 separate ones. I'm not sure. So this is actually timer 1 low, followed by timer 1 high. And then this is T1 low order and high order latches. I'm tempted to make these actually. No, you know what? I'll just keep it like this. I might end up unioning these with a 16-bit value. We'll see. We'll see. And this is timer 1 low latch. And timer 1. Or maybe I'll do it like this. Latch low and latch high. Okay. So this is the T2 counter low, which is also a latch, but that's a detail. And timer 2 high. Got the shift register next. Shift reg is fine. Auxiliary control register. Peripheral control. Interrupt flag register. Like, I'm looking at these names here and almost wondering whether I should just start using these. We'll see. Interrupt. Interrupt enable. Output register A, input register A. What's this again? Same as register 1 except no handshake. Really? So I don't know exactly what that means. So what does it mean, handshaking? In this, oh, here we go. Handshake control of data transfers. Looks like it is some kind of protocol even. Interesting. The R6522 allows positive control of data transfers between the system processor and peripheral devices through the operation of handshake lines. Port A lines, CA1, CA2, handshake data on both a read and a write operation, while the port B lines handshake on a write operation only. Read handshake. Positive control of data transfers from peripheral devices into the system processor can be accomplished very effectively using read handshaking. In this case, the peripheral device must generate the equivalent of a data-ready signal to the processor, signifying that valid data is present on the peripheral port. This signal normally interrupts the processor, which then reads the data, causing generation of a data taken signal. The peripheral device responds by making new data available. This process continues until the data transfer is complete. In the 6522 automatic read handshaking is possible on the peripheral A port only. The CA1 interrupt pin accepts the data ready signal, and CA2 generates a data taken signal. The data ready signal will set an internal flag which may interrupt the processor or which may be polled under program control. The data taken signal can either be a pulse or a level which is set low by the system processor and is cleared by the data ready signal. So I have no idea if this is even used by the Vectrex. It sounded like maybe it wasn't. So, and here, what I'm getting, if we go back to, where was it? This table. That this would be a way to read or write to A without engaging this handshaking stuff. Just look back at my notes. See, like in the time that I was recording reads and writes, these were never even touched. I'm going to assume for now that it's not ever engaged. I'm not going to put anything for it, and I'm going to assert on any read or write to that offset. Okay. All right. So let's say we've got that. Just split this here. Okay, I'm gonna just zero out all my data here. I think I'm going to remove the reg. All of these are registers, basically. Okay. Why did it say 6? 1, 2, 3, 4, 5. Okay. Let's do this for now. Okay, so now for reading and writing. So yeah, this is going to be a bit sucky because I need to like switch on all of this, but for now it's okay because I think I'll want to know when we write the specific bits and stuff. So that's all right. Let's do this. Let's so that's the register index. Actually, what I might want to do here, no, it's all right. I'll worry about that after. It's 2. You know what, let me copy this. Right, and we don't have a case for 15 just yet. I'll actually say what it is. No A without handshake not implemented yet. Okay. And similarly, we'll want to do something here for write. Instead of returning all these returns, just remove them. And we'll want to set them all equal to the values. For now. That's cute. Oh yeah. Won't go far without putting breaks in there. So let's look for, oh no, return is fine. Here I need my breaks. So if I've got value this, replace with value break in the selection, reformat, Okay, so let's see here. See if this compiles. Right. Let's do that. I will put a break here just to be clean. Okay, looks like it builds, and really this should have no change. But so if you haven't seen this, Michael C, this is what my Vectrex emulator does so far. Is it is able to run, and I've got a CPU implementation that's nearly complete, but has enough instructions implemented to correctly run the BIOS, and including the built-in Mindstorm game, although I don't know really how far it gets. I know that it's rendering lines and it's writing text on screen. It's probably at the title screen. I haven't done any drawing yet, so I have no idea, but looking at the trace, I'm able to kind of guess. This is also a debugger, which has like a bunch of things it can do. And one of those is I can disable the trace here and just kind of run. This will run a lot faster because it's not outputting anything. Turn on the trace again. You can also colorize, which is nice, but it's slow. So yeah, basically looks like it's running as before. Why am I getting an out of range exception and not actually breaking on it? That is a little disconcerting. Standard out of range. Let's go with restore to list of default settings. Here. Michael says, nice stuff. Thanks, man. So am I really hitting this? Because I'm in release. But which part is throwing the exception here? Let's see. Where are we at? You know what? Let me run this in debug. Let's see what this looks like. Turn off trace. We'll see if we get this in debug as well. I'm also paying attention to the output window here because that's where I saw that we were getting these exceptions. We should be definitely hitting here. Yeah, there's a breakpoint there. Got an index of 0, so we're reading B here, so we're just going to return B. Where are we now? Okay, so when I hit Control C, oh, okay, maybe that was what happened. I'd hit Control C. Control C, oh yeah, there's Control C. That's okay. We don't really want to break when that one's thrown. So let's continue going with that. Trace. I'm wondering if this is something that only shows up in release. We're not really getting anything. Let's try again. See what happens now. Trace. I was definitely getting the out of range exception though. Anyways, I'll just continue. If it'll show itself again. All right, so I have this. Okay. Let's just get this committed. So via replace register buffer with 16. Let's say 16-byte buffer with actual registers. Register variables. Okay. So next, what should I implement here? I think what I can start doing here. Let me just pull this out again. Just thinking what I should be doing here. I'm thinking if my next step is to start dealing with getting an OpenGL window up and running and start rendering to it. Oh, so Michael answered me. He says, I've been working on a PS1 emulator recently. it's really basic now, but hopefully I can get a lot of the CPU implemented. Man, that's really cool. I think you might have mentioned that on Ferris's stream at some point. That's really, really cool. Have you written an emulator before? Because I imagine emulating a PS1 isn't that easy. You did some NES emulation. Same. Yeah, I wrote my own NES emulator a couple years ago, and it was really fun actually. And yeah, that kind of is one of the things I realized, that I love writing emulators. The number of instructions annoyed you? You mean on the NES? There are actually more instructions to implement on the Vectrex's processor. Isn't it similar for the PS1? Doesn't it have like, it's not a complex CPU with a bunch of instructions to implement? So I want to get a basic, like the most basic OpenGL window open, and I've done that before. I have some code for, like old code for getting that done. I'm wondering if I should make use of something that does it for me. Like, does SDL, I didn't do OpenGL with SDL, but does it like support it kind of out of the box? Oh, yeah. That's nice. The PS1 has about 67 instructions. Is that like 67 with all, unique instructions where like there's a bunch of addressing modes and all that, but the actual unique instructions are 67? I don't even know actually how many unique instructions I have for this processor, because I have this table, but there's obviously lots of duplication in here for all the different addressing modes and all that, but there mustn't be very much. Anyway, okay, so SDL, I was more interested in SDL2 OpenGL actually. Very basic SDL2 OpenGL application. Yeah, PSX has a very simple ISA. Well, that's good news, right? Shouldn't be too bad writing that. I guess the complexity with the PSX is it's going to be mostly about rendering. I know that one thing I remember is, I think it's the PS1 that doesn't do perspective correct texturing. So I don't know like how important it would be to simulate that, but if you want the games to look the same, I guess you'd have to write like you're either a software renderer or a renderer where you get to do the not perspective correct texturing in the shader or something. I haven't given it too much thought, but it sounds like a fun challenge. And I guess there's also emulating the CD-ROM, right? You were planning on doing a software renderer? Okay, that's cool. Yeah, I guess that's another complication is emulating like disk access and seek speeds and all that. I don't know how important that is there. I mean, I guess you could just pretend there is no seek speed and all that. I don't know how much games rely on it. So STL init, STL window, renderer, render info. So create window and renderer. Get the render info. Check that we have OpenGL. Okay. Display init GL, set the viewport, display render. Okay. You don't really need a renderer in STL2. Delete everything else. Okay, so this is kind of a sucky example. This is simpler. This is even better because this has an event loop. Okay, so I just want to see if I can get one of these basic programs up and running, and then I'll migrate what I need into Vectrexy. I actually have, we're speaking of the NES emulator. My NES emulator used my NES emulator used SDL2, and I have some nice CMake crap for that, so see if I can get that working again. Okay. We'll just call this SDL GL test. So just copy this. And this find SDL2, because that's what I needed. In my source folder, I will grab this guy. So there it is. SDL/GL test. Do I need any of this? Sure, why not? All right, so to find SDL2, use the find package. I even have a post build step to copy SDL2 DLL. That's cute. I forgot about that. Okay, so let's see if this even works. Make dir build. I should get an error because of SDL2. I just want to see it actually happen. All right, some warnings. Okay, could not find SDL2. That's fine. That's what I expected. I thought it would say what I had to do. On Windows, I wrote it here. Set SDL2 environment variable to the path to the SDL2 development libraries route. Now, I actually think I have it right here somewhere. Yeah, I have some version 2.0.4 here. So that's fine. So what I'll do is I'll say set SDL2. Is it equals? Yeah. To that. And then let's CMake again. All right, found SDL2, configuration done. So I should have, yeah, SDL/GL tests.sln. So I'll open that in Visual Studio. It's opening on my other screen, just 1 second. Oh, here it is. So what does this look like? Look again at how this guy works. Yeah, I think this is maybe for Mac. If I recall, on Mac you prefix with SDL2, but on Windows you don't. This is like an annoying problem with how SDL works on the different platforms. Okay. And this here also is a Mac thing, OpenGL. I mean, it's nice how Mac has these like packages and frameworks and all that, but it's not nice how for C++ it's not easy to get it to be cross. Is it GL? It's been a while, yeah. GL on Windows, OpenGL on Mac. So is this build? Looks like we're missing a include Windows. Or something. What is this? WinGDI API? It's from the Windows kit. Really? It was indeed that. And then there's a couple of warnings. Do I have warnings as errors? I do. Let's see if this runs. Oh, now we've got linker errors. Right. I need to also link against OpenGL. Not sure what the right way, or what the, yeah, what's the most cross-compatible way to do that? CMake OpenGL link. All right, CMake linking OpenGL and glut. Find package OpenGL. Let's try that. And then I need to do this. This sounds, yeah, I think this is using the old way of doing things, but let's just see if this works. I'll start with that. All right, found OpenGL. That's good. It also showed that we needed to tell it to link against OpenGL library. Target link libraries. So we've got SDL that, SDL2 library, and then OpenGL library. Reload the solution. Okay, getting closer. External, unresolved external symbol. Okay, this is GLU. Do I need the GL utility library? He's using it for perspective here. Just out of curiosity. Actually, isn't that part of glut now? This actually might be fixed by this. Oh, thanks, Michael, for the follow. Appreciate it. Okay, so let's do another. I think GLU is part of glut, if I'm not mistaken. We'll find out soon enough. Michael C says, no problem, I'm gonna be heading off now. See you later. Thanks, man. Thanks for hanging out. So let's see if this builds now. Okay, no. So it's not really part of glut. Oh wait, could not find glut. Okay, because I don't actually have glut set. But all right, let me see here. CMake GLU. What does it say? GLU is neither part of OpenGL nor Qt. You must add it as an additional dependency manually. The CMake find OpenGL module also searches for GLU. Ah. Okay, so I can just say link against OpenGL GLU library. Simple as that. Let's take off glut. We'll add this as well. Okay, cool. Awesome. And here we are. It works. Okay, this is great. So I have a way now to get this injected into our project nice and easy. I was thinking before I do that, I'll try and modify this guy to just before I do anything, I think I'm gonna make a little commit of what I have here, because it's nice to have a simple way of creating a an SDL with OpenGL with CMake as well. It's kind of nice. Oops. SDL. Why do I have a Win32 folder here? Okay, so little git ignore build. Don't like how we're getting these ridiculous folders here. I think it's fine, like this. Just set my stuff up. I always force myself to set local variables for email and name because I have different email accounts and projects, so I don't want to set them up globally. Okay. All right. So now I can modify this to my heart's content. Skeleton. Yeah, I need to regenerate this because I renamed the folder. Delete the cache. So actually, you know what? I'll be right back. Go to washroom. And I'll be back soon. All right. Okay, all right, back. So, let's see now. Did this not? Oh, I gotta set my SDL again. Oh, let me stop the music. As much as I love the music, I think it's not as fun for people trying to listen to the stream. Okay. So this should build again. And should run. Oh, sorry, wrong target. Set a startup project. F5. Okay, so in our case, let me just look at this because this is all got global variables and stuff. It's all right. So technically what we have is a 256 by 256 screen, but non-square. I'm not going to worry too much about how to make it look right, but I think, you know, it's not hard or anything. I just need to decide on what window I want, and it's really about the mapping with the viewport. And I'm only dealing in 2D, so I don't have to worry about any perspective or anything like that. It's just going to be straight up 2D mapping. So like here in the set viewport here, we do this. And I don't really need to do it this way. I can just do a GL frustum. And if I recall, all I gotta do here is just set left and like left to 0, right to width. Oops. Bottom will be the height. Top will be 0. And then near and far, -1 to 1, I think is fine. So I think if I do it this way, then whatever I render, like basically my space will be in the 0, in this case 0 to 640. And in fact, if I want it to be is it, trying to recall, like if we set the bottom to be the height and the top to be 0, you know what, I'll just draw something and we'll see. So we don't need to translate. We'll start with a simple triangle. And yeah, let's go from like 0 to, say, 100. Yeah, I can't really go into the negative here because I'm not centered around 0, 0, 0. I'm even wondering if I want that. I could do that. Since the Vectrex is centered at 0, 0, I could actually map it that way. Maybe that'll be more interesting. So if that were the case, okay, so what we're looking at here is more like something like this. So half width and half height. The half width and half width like this. That'll be left and right, which will make 0 in the middle. Bottom will be half height. Top will be minus half height. Okay, so if I do that, then I can just kind of multiply these all by 100 to see what we get. Okay, let's see if this actually works. All right, getting all white. Okay, that's the STL window here. And set viewport. Yeah, so 320, minus 320 to 320, and 240 minus 240. Let me just put these back to 1 just to see. Interesting. Interesting and a bit surprising. Why? I thought, unless, no, that's right. I'm setting up my projection matrix here. And I thought if I set up in Frustum mode with exactly the same dimensions as those of the window, we'd get a one-to-one mapping of, like, you know, the pixel to pixel. And yet, when we render, it's like 0 to, basically we're getting a 0 to 1. So like this is 0, 0 here, and 1, 1 down here, I think. Yeah, exactly. In fact, not quite, right? 0, 1, so it's like actually 2 by 2. What am I missing here? And like if I put 0.5, makes sense. I mean, it makes sense in the sense that it is what I said. It's a 2x2 grid that I'm dealing with here. It's completely not what I expect. So I set the viewport, which maps this space to the screen, and then the frustum sets up the projection. Oh, no, it's not frustum that I want. Okay. What I want is an ortho. That makes a lot more sense. Left, right. I should have realized setting that I was setting a frustum and I was setting the Z near and Z far, of course. It's been a little while since I've done OpenGL. Okay, so let's see what this looks like now. Okay, yeah, so now it looks like I have a tiny triangle, which is more what I would have expected. So like, actually, let's do this. So this was 1 before. Like, let's scale everything. Can I just do that here? By generally speaking, I don't like using scale, but no, you know what? I won't do that. Let's just multiply it in. No. I'm gonna say, so we said it was 480, so 480 divided by 2. We're gonna go to negative 640 over 2. To same thing. To minus 480 over 2. Yeah, actually this is kind of gross. Which is the same thing as before. Alright, so this will be, all these ones here will be replaced with half height. And these guys here with half width. Okay. Yeah, and this is what I thought would happen. It would end up being flipped. Now, on the Vectrex, I don't remember which direction Y goes in on the Vectrex. Do I have something about that? Maybe in my notes. I do not have information. But so the reason why it's upside down is because of the way I mapped it in my ortho 2D. What I might want to do is consider the bottom as negative and the top as positive, which would mean that Y moves up as it goes positive, which might make more sense actually, now that I think about it. except that in 2D often y negative goes down. But I'm pretty sure the Vectrex goes more with a Cartesian coordinate system. So it'll make more sense to go like that, and it'll be more natural in OpenGL. So, and there we go. So now we've got our triangle. And just to make sure, if we scale it once again, we should get a triangle that's now half that size. Yeah, that looks about right. Okay. So this is basically the kind of setup we want. Specifically, there's also the concept of the difference between the size of the window and then the size of what we're rendering to. So yeah, like see, like here I'm assuming screen width and screen height. Yeah, that's okay. And we can be like, you know, like this could be bigger, you know. So like, for example, if I say that this is actually 640 by 480. But this becomes 256 by 256. And when we create, this become, instead of screen width, we'll call this window width. I kind of like that better because we're actually creating a window here. So that gets us this here. Does this make sense? This is 640 by 480. And this is 256 by 256. It's not actually being stretched the way I would have expected. And that's probably because of this here. Display set viewport. Yeah, actually this should also be window width and window height. Oh, no, I'm missing something here. I'm not actually doing anything with this ratio. Yeah, so what I want to do here is I want to what is it I want to do? I want to map the screen width and height to that of the window. So kind of like not take the actual width and height of the screen here, but always map, you know, this guy here. I think that's what I want. Yeah. So we're saying that the projection matrix, I mean, the projection matrix will be set up in terms of screen width and screen height, the 256 by 256 that we want. And then that gets mapped fully into, yeah, I think that's right, to the size of the window. So we basically separate the two. Yeah, that looks right. And see, like, there's a bit of a stretching that occurs here, and which makes sense because 256 by 256, which is square, is being stretched here. Like if I make this window width if we double it, we get that. So that's perfect. So now what we would want here is we'd want to figure out what the actual aspect ratio is. Like, we'd want to make our window size something that makes it look like the Vectrex. So what is our aspect ratio for the Vectrex? I mean, I think it's 3:4, because from what I read, the Vectrex just had a regular TV screen that was turned 90 degrees. Let me see. Give me a second. Any information on the actual screen size here? Dimensions. It's a 9-inch CRT, okay. Okay, so here's something. 9 by 11. .22. Really? Yeah, that doesn't sound exact. What was that I was seeing here? 9 3/4 by 11.5 by 14.5. Anyway, whatever. I think it's supposed to be 4:3. So like, what I'd want is a way to like eventually be able to resize and kind of keep that perspective. So for now, something like, you know, if we actually swap these, this is just right off the bat, this is 4:3 there. In fact, what I can do is we'll set the, what's easier to set? We'll set the width and then the height in terms of the width. What is it, 3/4? Um, 480 times 3/4, is that right? No, that's not right. It's 4/3. Of course. So now that looks more like what a Vectrex would look like. And 0, 0 is in the middle. And we should be able to go to minus, you know, I mean, close anyway, minus 128 to positive 128, and minus 128 down and y to positive 128 in up here. And, you know, we can try different ones here, like I'm trying to think of what are like, what I'm trying to remember the common, 640 by 480, there's 800 by 600, right? 1280 by 768, I think, is the next one. Yeah, that's pretty nice. 600. We can just run with that for a little while. And ideally, if you resize, what I would do is I would like to do that kind of thing where resizing keeps it snapped to a fixed aspect ratio, which I think is a bit complicated to do in OpenGL, but whatever. Not necessarily with OpenGL, I mean complicated to do with SDL. So I think I have enough here to start getting this integrated into the Vectrexy. Just looking at the time, I'm thinking that I think this is probably a good place to stop. Feeling a bit tired. What I'll do is maybe I'll start moving this into Vectrexy over the course of the next few days, or if I don't have time, well, I'll just resume this on the next stream. So yeah, I think that's what I'm gonna do. So thanks for watching, and I'll see you guys next time.